Alright, so this lesson's about electrostatics. Now you're going to find for the most part this stuff is fairly low level compared to what we've been looking at, but there's a bunch of it because it's kind of an introductory lesson. Alright, so electrostatics means when you have unbalanced charges, which means you have something with either more electrons than protons or more protons than electrons. Now, protons and electrons are known as elementary particles or elementary charges. The charge of a proton is positive 1.6 times 10 to the negative 19th, and the charge of an electron is negative. This is what's given to you in your reference table, basically the charge of an elementary particle, and electrons are negative and protons are positive. Now you're going to have a negative charge if you have more electrons than protons, and you're going to have a positive charge if you have more protons. Alright, so if I have two objects that are positively charged, they're going to repel, because like charges repel. Same thing as if I had two negatively charged. And if I have oppositely charged, they're going to attract. Now the force on each, that force is equal to this force. Okay? Kind of like with gravity, the force of attraction is equal. In this case, the force of repulsion is equal, or attraction. Now neutral objects are actually attracted to both. So if I have a positive charge and a neutral object, they're going to be attracted to each other. Same thing as if I had a negative object and a neutral object. They're also attracted to each other. Alright, keeping that in mind, let's look at this example right here. I have two small hollow spheres hung on an insulating thread. So basically I've got two metal spheres and there's some sort of thread that's not metal attaching them. And we know that a positively charged rod will attract A. So that means that if I have a positive charge, A is attracted to it. Now that could mean two things. A could be negative, or A could be neutral. Okay, so A cannot be positive if it's attracted to the positive. A has a negative charge. It could, but it doesn't have to. And A and B have opposite charges. They could, but they don't have to. You could have positive and negative, but you could also have positive and neutral. So none of these have to be true. 2 and 3 could be, but none have to be. Alright, so here's a nice small equation, beautiful equation, wonderful equation, not in your reference table equation. Q equals NE. Q is the charge of an object in coulombs, N is the number of excess, and E is the charge of one electron or proton, one elementary particle. So E always equals 1.6 times 10 to the negative 19th. It's a constant like little g and big G and all those. Okay, so let's think about this. This equation makes complete and utter sense. If I had, let's go with 10 nickels, and I was to ask how much money I had, you would tell me I have 50 cents. How did I get that? Well, I multiplied the number of nickels I have, which was 10, by how much each one is worth, which is 5 cents. If I was to do that with charges, I would count the number of excess I have times the charge of each one. Q equals NE makes perfect sense. Let's look at some examples down here. Now, this sphere right here has 6 positives and 6 negatives, which means N, being the number of excess, equals 0. So Q equals NE. Q is equal to 0. That means it's a neutral charge. The bottom one here has, let's go with 6 protons and 9 electrons, which means N is going to equal 3 because that's how many excess I have. So if I was to plug that into Q equals NE equation, I would have 3. Now it has excess electrons, so that's negative 1.6 times 10 to the negative 19th. And I would get 4.8 times 10 to the negative 19th coulombs. The units for charge is coulombs, that's a capital C. And that's a negative 4.8. Now up here I have n equals 3 again, but it's 3 extra protons, so the charge would be positive 4.8 times 10 to the negative 16th coulombs. Okay, now, there are two types of materials. There are conductors and insulators. Conductors allow electrons to move freely. It's that whole sea of electrons thing, while insulators do not. I always think about it as, in insulators, electrons are in leashes. They can move around, but they can't move very far. Conductors like, go, run free, have fun. Alright, so taking into account this slide and the one where opposites attract and likes repel, let's look at this. If I have an insulating sphere and I bring a negatively charged rod nearby, all the electrons are going to be repelled. Protons will be attracted. Alright, so protons don't move. And that's basically how it is, because protons are mass. Mass isn't going to move. The electrons are the things that move. So your electrons, which were scattered evenly, are now all moved away. This is known as polarization. Now they can't move very far because they're on a leash. But this polarization is what allows neutral objects to attract, because basically the positive is closer, so there's an attractive force there. Now if you have a conducting sphere, so if that same sphere was conducting, what would happen is all the electrons would move to the far side, and they'd be free to do that. They wouldn't have to kind of stay where they are. They would just all be able to move completely away. Alright, so I've said this. Electrons are the only type of charge that move. Protons don't. Protons have a lot of mass. They're the core element of matter, which means they basically have to stay still. If you want to move protons, you actually have to move mass. And overall, the number of protons and electrons in a system doesn't change. So protons and electrons can move, but they don't suddenly go poof. That is known as the conservation of charge, or the law of conservation of charge. Alright, so we're going to explore how charges move using this apparatus right here. Now this apparatus right here is known as an electroscope. Basically, it's a metal conductor that is connected to two metal leaves. So metal means that electrons are free to move. So as a negatively charged rod is brought near, the electrons are repelled away and they kind of gather down here at the bottom. So both leaves become negatively charged, which means they repel from each other. So they're going to push apart. This is how you can tell if something is charged. If you bring it near and the leaves go apart, it's charged. Now, part 2 here says I'm going to touch the electroscope with my finger and the leaves collapse. Well, let's think about why that is. Well, if I touch it here, the electrons are still repelled away, but now they're going to be repelled down my hand, to ground basically, is what it's known as. So now, the excess electrons that would otherwise have been chased down here have now been chased out of the system. Okay, now, what's happened here with the third one? The third one, I have removed my hand and then the rod, and that order is very important. Alright, so I've removed my hand, which means there's no longer a ground. So the number of charges that were there will now stay, while the electrons have been chased away. So we now have more positive charges than negative charges, which means the leaves will be positively charged, making them repel again, because the electrons have left, leaving less negative behind. Alright, so let's look at our possible answer. Now the question asks us, what's the charge in the leaves? So in the first one, the charge in the leaves is negative, which means A is not possible. In the second one, it says that the charge in the leaves in 1 is negative, which is true, but in 3, the negative charges have left, so that means that's positive, so B is not possible. Positive in 1, negative in 3, no. Negative in 3, or negative in 1, positive in 3, yes. So our answer is D. Alright, conservation of charge. This goes along with the conservation of charge. Charge is not created or destroyed. If I have two metal spheres that are both positively charged and they touch, what's going to happen? Well, charges, like charges, repel. So what's going to happen is they're going to equally distribute. So you're going to end up with a positive 5 charge in each one. If I had a positive 4 and a positive 6. Now how do I get this? Well, the overall charge stays the same. So in the beginning we had a charge of 10. In the end we have a charge of 10. And they're going to be equally distributed, which means they're both now going to have the same amount. So what you should do is find the overall charge and divide it by the number of items. And that will give you the charge in each. So the overall charge is 10, and the charge of each sphere is 5. Now the question 2 asks you, which one gained electrons? Well, if we look at a number line, alright, this is 0, these are negative, these are positive. One went from 4 to 6, so it became more positive. Or sorry, 4 to 5. And the other one went from 6 to 5, so it became more negative. The positive 6 one actually gained electrons because it became more negative. Also, you think about it, greater positive charge, it attracts the electrons more. Now question 3 asks you, what if you had a sphere that was negative 6 and positive 4? Well, you're going to do the same thing. Your overall charge is negative 2, which means each one is going to have a charge of negative 1. Alright, second part of the lesson is Coulomb's law. Coulomb's law comes from the physicist Charles Augustin de Coulomb, and it looks at that force of attraction or repulsion between two charges. Now this equation is our Coulomb's law equation, or electric force equation. That basically tells us that K, which is a constant, times the charge of each one divided by its distance squared is going to be equal to the force. Now if I have two like charges, they're going to have a repulsive force. If I have two opposite charges, they're going to have an attractive force. And the forces are going to be equal and in opposite directions. So that force is equal to that force, except in the opposite direction. Alright, so here's a breakdown of what each of them mean. And here's the K for Coulomb's law, 9 times 10 to the 9th. Keep in mind, r is the distance between the charges, not half the distance. Okay, because r, people think radius and they want to go half. Alright, for an example, here's a question. Two elementary charges are experiencing a force of 2 times 10 to the negative second, and they want to know how far apart they are. So my F is 2 times 10 to the negative 2, or negative 10, equals K, which is 9 times 10 to the 9th, times the charge of each one. Now these are elementary charges, which means they both have a charge of 1.6 times 10 to the negative 19th. Now I can write that out twice, or I'm just going to square that number. Divided by r squared. Once you get here, it's just algebra. I recommend cross multiplication, and you get 2 times 10 to the negative 10th times r squared is equal to 9 times 10 to the 9th times 1.6 times 10 to the negative 19th squared. Solve for r, don't forget the square root, and you should get 1.07 times 10 to the negative 9th meters, or about 1 nanometer. Should be your r. If you did not get that number, I'd recommend you plug it into a calculator. Make sure you either use the capital E symbol or put parentheses when you divide it by that. Alright, here's a question. A sphere of charge Q is in a fixed position. A smaller sphere of charge Q is placed near. We want to know, as it moves away, how does the velocity and acceleration change? Well, acceleration is equal to force divided by mass. Now, as you move away, electrostatic force is Kq1, Q2 over r squared. So as your r increases and you move away, your force will decrease, which means your acceleration will decrease. So acceleration will go down. Now, you may speed up less quickly, so it's like your foot isn't as hard on the gas, but you are still speeding up, which means throughout that entire time, your velocity will be increasing. Alright, 2-point charges are spaced a distance x and exert a mutual attractive force of F. So, distance x, F is your attractive force. If the charges are separated by a distance of x over 5, what's the new mutual force? So F is equal to K Q1 Q2 over R squared. We start looking at the relationship. So if I was to put my R, or in this case X, is fine, over 5, what happens to my force? Anything that stays the same can basically cancel out, so force is proportional to R squared over 25. Now the R basically stayed the same, so that can also kind of cancel out, and you get F is proportional to 1 over 1 over 25, which means my force increased by 25. Because remember, 1 over 1 over 2 is equal to 2. So 1 over 1 over 25 is equal to 25. Alright, two identical conducting spheres, one of 3q and one of negative q, are a distance d apart. The magnitude of the force of attraction is equal to F1. So F1 is equal to K negative q 3q over d squared, because they called it d. Now after the two spheres are made to touch, they are then reseparated to a distance d, and you want to know the force. So F1 is equal to 3k q squared over d squared. Now if they touch, then you have a positive 3 touching a negative 1. Your overall charge is positive 2, which means they'll both have a charge of positive 1 in the end. So I'm going to call it F2 is equal to K 1Q times 1Q divided by D squared. So that is equal to KQ squared over D squared. The difference is a factor of 3. So it's actually going to be a third of F1. Now this is all fairly easy if you have only two charges, but sometimes you have more than two, which means you have to put those forces together and find the resultant force. Now if they make a triangle, you're going to have to use a squared plus b squared equals c squared. If they're linear, you're just going to have to add or subtract them, just like you would if you had multiple forces. For example, here's a question. As shown below, two particles each have a charge of q and are fixed opposite positions, and they want to know the magnitude of the force. Okay, so we're going to look at this little q charge, the force acting on it. I'm going to label it 2. So the charge 2 has two forces acting on it, one from 1, one from 3. So this is the force of 1 on 2, and this is the force of 2 on 3. Now they tell us that F is equal to the magnitude of one force on the other. Now as you can see, both these forces are the same, so that's F and that's F. Now if I had numbers, I could plug them in and solve. If I want to know the magnitude of the force, I say, okay, this 1 and 2 are repelling this way. 2 and 3 are repelling this way, which means I need to find the hypotenuse. So once I find this force and this force, I can just do a squared plus b squared equals c squared. So in this case, f squared plus f squared equals c squared. And you get the square root of 2 times f is equal to c. Alright, that's just as easy. You do the exact same things if you had numbers. This is an example of where you would have numbers. Just keep in mind this nanocoulombs means 10 to the negative 9th. So that's 40 times 10 to the negative 9th. And these are centimeters, so that's 0.6 and that's 0.8. And you would just basically find the force between these two, the force between these two, and do a squared plus b squared equals c squared. Now the last thing to address is the difference between electrostatics and gravity, or the similarities. Alright, gravity is always attractive, while electrostatics can be attractive or repulsive. But besides that, they're very, very similar. Both of them are directly proportional to either q or m. Same equation, just, different q's or m's. They both have an inverse relationship to r squared and an inverse square relationship to r. Okay, so they're both basically over the distance squared. Also an important point, k is greater than g, 9 times 10 to the ninth, 6.67 times 10 to the negative 11th, which means that with the same, let's say if q is 1 and m is 1, your gravitational force will be smaller. Also, interesting point, nuclear force. Well, if I have an atom and the center is made up of protons, why doesn't that atom break apart? That atom doesn't break apart because of something known as nuclear force, and nuclear force only happens when you're really, really close together, when these small particles are really, really close together, and it's actually stronger than the electrostatic force. Alright, and an interesting point as well, it doesn't have the same relationship with distance, or so we have found. Basically, if it's closer together, that doesn't mean it's stronger. There's just a point where it exists and where it doesn't exist. We don't completely understand that yet, but it's an interesting point. Alright, that's the end of the lesson. Good luck.